The overall goal of this protocol is to prepare conductive polymer nanoparticles that exhibit photothermal properties and evaluate their cytotoxicity.
Conductive polymer nanoparticles are ideal agents for photothermal therapy because they absorb light in the near infrared range and convert it to heat to kill cancer cells.
The main advantage of polymeric phototherapy agents is that they can be tailored to tune their absorption properties, biocompatibility, and tumor targeting ability to enable effective non-invasive localized cancer therapy.
The polymers we are using for photothermal therapy can also be used for alternative energy applications, sensors, and electrochromics.
Individuals new to this method may struggle because the reaction is sensitive to moisture. A good understanding of airless synthesis techniques is essential.
Visual demonstration of cell culture assays is critical, as sterile techniques are difficult to master. All multi-well plate assays require accuracy and consistency to achieve proper results.
To a 3-neck round-bottom flask, secure a septum, a condenser fitted with an inlet control adapter, and a gas outlet control adapter. Connect the gas outlet adapter to a bubbler. Next, connect the inlet adapter to an argon Schlenk line with thick-walled PVC tubing. Begin the flow of argon into the reaction flask and let the gas flow for several minutes. After turning on the vacuum, use a Bunsen burner to flame dry the reaction and then purge the apparatus with argon. Repeat this twice more to achieve an airless environment. Use a syringe to add 1.07 grams of EDOT to the apparatus through the septum. Add 20 milliliters of tetrahydrofuran into the flask and stir. Prepare a dry ice acetone bath in a low-form